Right, welcome. We are here to talk to you guys about developing modern applications in .NET Core. My name is Qiming.
I'm James Watson. So as the guys mentioned, we've come over from Adaptive in London. Sorry about bringing the weather with us. Not much we could do about that. So what are we going to talk about today? The agenda today. What is a modern system? It's kind of our version of that is a reactive system, and we're going to show you Reactive Trader Cloud, which we developed at Adaptive. We're going to talk a bit about messaging, a bit about .NET Core, and some Docker and Kubernetes.
Cool. A bit more on who we are. We are from Adaptive. We are a London consultancy. We have offices in Montreal and here in Barcelona as well. Day to day, we build trading systems, real-time trading systems for financial and commodity industries. So Reactive Trader Cloud, which we'll demo in a bit, is very typical of a system that we would build for our clients. So moving on with our agenda, let's start with what we think is a modern system. What do we mean by it? So what we really mean is, by a modern system, is that it has to be a reactive. What is reactive? So leading technologists in the industry have written the Reactive Manifesto, which says that a reactive system should be resilient, responsive, elastic, and as well as being message-driven. We'll delve a bit deeper into that soon, but that's all theoretically nice. But how do we actually implement such a system? And what we think is that microservices, which I'm sure you have all heard of, are a very good solution.
So what do microservices allow us in terms of these principles of reactive design? They are resilient because a single microservice going down won't bring the whole system down. They're responsive because, well, they're responsive because individually each microservice is doing a different thing. They're able to the way we've done it in Reactive Trader is that we've used reactive extensions everywhere. So everything, instead of being pull-based, everything is push-based. So for instance, we'll show you in a minute the screen, but kind of prices are streamed to your desktop. So what else the microservices allow you? They're elastic and scalable. We can bring up multiple instances of microservices, of the individual microservices, allowing them to share the load between them. And lastly, microservices don't live in isolation. We need to communicate between them. And in this instance, the Reactive Manifesto dictates that we need to use a message-driven approach. So that is that allows you to decouple communication between the services, and you just use a common message format to do that.
Yep, absolutely. Bit more. We'll show you the app very soon, but a bit more theory. We've already mentioned the benefits that are grayed out, and being individually responsible for the business functions of each microservice. They are also independently deployable, upgradable, etc. If you work on a very large project, you can split your team into managing different vertical slices of functionality. And again, microservices are a great way to help you to divide up your resources. What are the cons? Well, compared to a large single service, you now have more components to deploy. So that in itself is a potential ops management task that needs to be done. Again, we'll see later how Docker and things like Kubernetes allow you to manage that well. And also, as James mentioned, the common infrastructure will be messaging between microservices. So again, you need to build up a more complete communications infrastructure between them.
So just out of interest, as a show of hands, who's used microservices at work in a side project?
That's about right.
Yeah, that's about right.
Yeah. Cool. So So onto our demo project, Reactive Trader Cloud. It's a research and development project that we at Adaptive have open sourced. It is a real-time foreign exchange trading application, very typical of something a trader at a bank or a financial institution would go into work, launch, and use to trade. Broadly, it's built on a .NET Core backend, a React.js frontend, and the messaging is done using a brokered messaging system over WebSockets. We talk JSON. Like I said, it's built entirely on open source, which we think is pretty cool because typically in such a magnitude of application in the finance world, you would be paying 6-7 figures just for for example, the messaging middleware part. But this is our solution. We think that it can be done all with open source, and this is our demo for it. And yeah, it's a showcase of reactive principles across the whole stack, not just the UI, as well as the backend and config even. That's the GitHub link, which we'll have all the links at the end. So, first demo. Oops. So this is our live environment, which we have deployed. And here you can see the app.
So we've got, this is typically what you would see as an FX trader going into a bank. You are, for instance, buying pounds and selling dollars, and you have a price, different price to buy and sell. So on this screen, we have built in there are some of these tiles will deliberately slow down. You won't get prices for 5 seconds, and it will inform you. So if it goes red, it means that you haven't received a price. So what we've done is we've surfaced technical errors as business events. So this breeds a certain amount of trust between the user and the system that what they see on the screen is what is going on in real life. So on this screen down here, you've got the trade blotter. This is a list of trades you've done through the day. So if Qiming does a trade, that will pop up there. So we've also, as well as the error scenarios with prices, we've also got error scenarios with trading. So there's an example that's always rejected.
Yep.
So that tile will always be rejected. But there's also an example of a tile that takes 5 seconds to book. So typically a trader doesn't like that kind of delay, so they will want to know what's going on. So if this will take 5 seconds, it will go to a timeout. Eventually the trade goes through and the trade is booked. And on the right-hand side, there's the profit and loss. This is a aggregation of all of the trades you've done and the current prices.
So we are 26 million in profit. Not bad. Cool. Yeah, so again, this is a real-time report for the trader of how much money you're making or losing. And the idea really is that everything is real-time. Everything is pushed at you, and we give our best effort to give you the accurate information, regardless of any technical issues that we may have.
So we've not only done this as a web front end, we've also got an iPhone app that if I do a trade, you can see that popping up on the screen there. I mean, it's on the App Store if you want to play around. But I mean, once you've done one client, the way our broker works, you can do it with anything.
Sure, it's a WebSocket connection over with JSON to a cloud endpoint. So we also have the traditional WPF apps. I think we even have a WinRT app, which I'm not sure is being maintained anymore. But yeah, cool. So this is a photo of the app. So in terms bringing it back to microservices,
In this example, you've got the reference service that provides you your price tiles. You've got the price service that provides all of the prices. You've got the trade execution service. That's when you press a button, when you press the trade button, that's what's booking the trade. You've got the trade blotter service at the bottom, and you've got the analytics service on the side. Too far away.
Yeah.
So each of these, so we've got 5 different microservices, each as an independent unit.
Cool.
So now that we've covered that, we've got another demo.
We'll change to an environment that we can break. Yeah, so now you've seen how the UI breaks down into different functional microservices. We can start playing. For example, I don't know if you can see, but on the bottom right of the app, we have a status indicator. It shows which of the backend microservices are up and running, as well as how many instances of each service there are. So currently, we have 1 node each of pricing, reference data, blotter, execution, and analytics. And now, because we are in a actual microservice environment, we can now play around and see how it behaves to failure scenarios, which are much more interesting than happy paths. So, for example, we can start by, so this is a control panel that I can use using Kubernetes. We'll go into that a bit further in detail later. For the moment, it can bring up, down, up and down microservices. So we can do something like we can scale for the dev environment the trade execution microservice and say we want to kill it. We want to get rid of everything. We want 0 instances of it. What happens? We can fire that. And in a second, that goes yellow. It tells you we no longer have the execution microservice running, which means when I hover over, I can no longer trade. This is a partial failure scenario, but we want to support as much functionality as we can. So you can still see your prices, you can still see your trades, as well as your profit and loss and how much money you're making. Let's carry on. What happens, say, if we want to kill off pricing? Oops.
So the effect of this is going to be a bit more obvious.
Okay. We no longer have prices, which makes sense. The service isn't up. If we still see numbers, then we're in trouble. Yeah, again, as much partial support as we can give. Perhaps there are back office in the financial term. Back office are teams who only want to know about the blotter, who only cares about a list of done trades, and they want to print charts or reports on it. We don't want to bring them down. If there was a monolithic single component service, say one of these components throws an unhandled exception, everything will go down. So this is a key benefit of a microservices architecture. So let's bring everything back up. Right, so now we've seen partial support. Let's try elasticity and scaling. So we remember that's part of the reactive manifesto. We want our system to be elastic and scalable. So instead of 1 node of each microservice, here, we can perhaps spin up more. So I will bring up Visual Studio. So this is a good time to pause and explain our backend. So each microservice is written in .NET Core, built as a Docker image and run with Kubernetes in Google Cloud. However, you can do all your dev work locally in Visual Studio, no difference to any traditional C# application. So in here, I have set up my local box to connect to that dev instance that we saw earlier. So if I spin up a local, it's over here, a local service. These are very plain .NET Core console apps, nothing special. So you can see that it has connected to the cloud instance, and is now connected to the broker as well as event store, and is now publishing data. So if we go back to the app, we should see, hopefully, there are 2 nodes of the blotter running. Because I've spun up a second node locally, this client will still be connected to the first instance in the cloud. So now we can try failover. So if I bring down the instance that we have in the cloud, 0, we should see blotter going from 2 nodes to 1 node, and then on my local instance saying get stream request from client. And I don't know if you noticed, in this corner of the screen, there was no flicker in the UI. There was no pauses, no spinners saying wait. It was a completely smooth failover. Just to prove that was the case, if I kill this one, then I no longer have a blotter. Both the cloud one and my local instance are down, and I no longer have the blotter functionality. Cool. That's it.
So, a bit more on this message-driven principle. The Reactive Manifesto says that the system needs to be message-driven. So what does that mean? That means each of the microservices needs to be able to communicate with each other using messages. So that is going against the standard kind of RPC call, and it's going more to serializing an object, adding it to a queue of your receiving microservice. So for Reactive Trader, we need 3 paradigms, 3 ways of communicating. We need to be able to kind of build on top of the underlying protocol and do request response. So that's fairly obvious. Request stream, so this is when you need the pricing. You send a request to subscribe to the pricing, and you get a stream of prices. And then pub sub, so this is a publisher publishes onto a well-known topic, and a subscriber subscribes on that well-known topic. So the real benefit of message-driven design is, or this message-driven principle, is that you're decoupling your publisher from your subscriber. So your microservices, as long as that protocol, that contract between the services is there, you can develop independently. So going into detail about how Reactive Trader works, we have seen these microservices before. So the key services that need data from other services are the trade blotter. So the trade execution service, that's the service where you do a trade, passes trades indirectly to the trade blotter service, but also the analytics service. This is the aggregation of all of your trades, needs data from the pricing service and from the trade execution service. And everything talks to the client. So as we saw before in the demo, the client is talking to each of these individually. So we need a contract, we need a set of messages to define that communication. So we went down a route called WAMP. This is the Web Application Messaging Protocol. It's an open standard. It runs over WebSockets. It's got quite a few clients. The clients we've used are kind of JS, iOS, Android, WPF. It does PubSub and RPC out of the box, and it basically works. You have a broker that sits in the middle of all your microservices. So the microservices only know about the broker, and they all connect to it and send messages to each other that way.
the dotnet library that we're using on the back end is actually a net standard library. So any net core app can use it. We use crossbar.io as the broker implementation. It's the most mature broker implementation for WAMP, and it's itself actually written in Python. So for Reactive Trader, we again simply place that Python app inside a Docker container, deploy it, and then we're done. So with a broker, what does our architecture look like now? Again, if you remember previously, these are the messages that we need to get across between components, and obviously that's quite messy. We ideally don't want a client to have to make connections to 5 different endpoints. So with a broker messaging system, that is much, much neater. Each component only needs to connect to the broker, and that's it. That's all we need to do for that.
So you could say it's a downside, but I don't really think that's the case. The client needs to be smart. It needs to know how to discover services. So the client's connecting directly to the broker, and it needs to work out what services to connect to. So this could be 1 or more services, or 0 or more services. So we've handled that so each service sends heartbeat messages to the broker to a well-known, this is where pub sub comes in. Each microservice sends a heartbeat message, and the client picks that up, builds a map of all the services that are available, and sends requests to whichever one has the lowest load as reported by the server. So it means the client needs to be a bit smarter, but it works as it's a nice, simple strategy for managing failover. It does the job.
Yeah. So again, we want a system that's easy to understand, want a system that's easy to write, easy for new people to pick up, and as risk-free in uptime as possible. So for example, going back to the broker slide, we have the central broker instance, which we can replicate and scale. However, we want as little logic in the broker component as possible because everything connects to it. So leaving...
It seems like that diagram, it's a single point of failure.
We will come on to that later.
So we're coming on to that later.
But yeah, so putting mechanisms such as a failover load balancing inside a client is a very, very simple way to achieve something that may on the surface seem quite complex. So in the demo, when we failed over from one blotter service to the other, the client first recognized that it no longer had connection to its first blotter service, but my local blotter service was pushing messages onto the broker saying, I'm here, I'm available. So then the client is able to tell, there is another blotter service available, let me connect to it. And that's how we do failover, as well as load balancing, because on the heartbeat message, each microservice actually publishes its own load to say how many clients are connected to it. So then the client can selectively select the lowest load instance. State.
So in an ideal world, we always want services to be as stateless as possible. In this instance, we did this with Event Store. So Event Store, for those of you, actually, show of hands, has anyone seen or played with Event Store before? So yeah, it's about the same group. So Event Store takes the place of our SQL database. So the idea is that it represents a central log of the system. You push events to it, and any service that's subscribed to it receives those events. So this allows you to build up it allows you to build, each service can connect to Event Store and subscribe to all the events, build up a picture of the state of the system.
Yeah, the key here is that Event Store keeps a serial log of every event that has ever happened, which is ideal for our case because we want the ability to shut down microservice and bring them back up. So because we have a continuous log of everything that's ever happened in history, each microservice launching a startup can load everything and be rehydrated with all the state that it needs. So that's why we don't keep any states in microservices, and the state that we have in them, we can recreate whenever we want to.
So this ends up, this is the complete picture of the architecture of the system. Just added, in addition to the broker that we added before, we've got event store. So these arrows actually represent whether or not the services are kind of read or write models. So the only thing trade execution service does is write to event store. And analytics service, trade blotter service, and reference service all subscribe to events from the event store.
Does it scale, is the question everyone always asks. And the answer is hopefully yes. So previously, again, the broker seems to be a single source of failure, because you saw that we can spin up more instances of each microservice. But we can scale any number of those sub-modules of the broker with microservices as we want, as long as they are all populated from the same source event store, because of the fact that they are stateless themselves. So in this diagram then, we can have as many of those as we want to handle load. And for event store, you can deploy a clustered event store that will replicate reliably across every node. And we really also, if performance becomes an issue, we really want to fine-tune the event store to only store the key business events that we actually care about. And any other events which are not so relevant, we can put somewhere else. We can put in a SQL Server database that we can retrieve later if we need to.
So what this means is, at the moment in the event store, we store the entire list of reference data and the trades. That's all that's in event store at the moment.
Cool. So .NET Core, finally. I think, yeah, you guys, everyone's played with .NET Core. Yes? Brilliant. So advantages, preaching to the converted. Cross-platform, runs everywhere. Biggest win for us is Docker. Windows containers aren't as mature as the Linux ones, as you all know. So the tooling around it is also less mature. So running on Linux is a massive win for us. C#, we love C#. It's an awesome language. It's the best language. And again, tooling now has caught up. So you get the same familiar Visual Studio experience as you would get in a traditional C# application. And for library authors, Net Standard is finally a decent way to build your libraries from, and also a rich open source community. When we started Reactive Trader, it was, I think it was beta 7 or 8 or something. That was still DNX days. We actually started off on mono because we weren't sure we could get all the library support that we could get. But then the community help has been really good. I'm sure some of you guys are on the Slack channel for .NET. And the openness of the GitHub system really helped us a lot. I think we were asking WebSocket questions to Stephen Taub and getting an answer in 5 minutes or something silly. So that was a really good experience. The tooling was flaky, but it has settled down until the CS proj migration, I guess. But when that comes, we will well, that's in the VS 2017 RC, I think. We haven't moved on to it yet for Reactive Trader. I think we'll do the move when Visual Studio 2017 comes out of RC. Move on to Docker. So now that we know that .NET Core can run on Docker, we are happy. We can play. So anyone, where we should have showed Docker? I think, yeah. So yeah, deterministic. Biggest win for Docker is that we are confident that our app, if we can run locally, it can run anywhere. The worst thing as an app developer is if your app runs perfectly locally, test or pass, deploy, no idea what's going on, no idea why it's failed. I think we've all been in that situation before when someone else has done the deployment for us. So Docker is really revolutionary in helping us to achieve that. Compared to VMs, it's very lightweight, it's very fast to spin up and to tear down, which means you can use it at dev time. For example, for Reactive Trader, if I want to test my application locally, and I've written my .NET Core services, I want to say to the front-end guy, give me a copy of the front end. I want to build it and test it against my client, against my backend. And he was like, okay, clone this code, run npm install, and then run Webpack, for example. So I do that, npm install, red everywhere. I have no idea what's going on. It's npm, it's non-deterministic, I don't know. And he was like, oh, which version of npm do you have? I was like, I don't know. Version of Node or npm? But then I don't need to have any of those worries. He can tell me exactly which version I need. I don't need to install it. I can download a Docker container. That's the npm image. I can build npm run inside that image, and then I have my web client artifact, and then I can run locally. I don't need to mess around anything locally. Similar for a front-end guy, he doesn't need to install .NET. He doesn't need to install Visual Studio. All he needs is Docker, and he can download the server artifacts, run them locally, and away he goes. So huge, huge development time benefits, as well as production time benefits. And how do you actually use them once you have them? So containers are all well and good, but you need a good way to orchestrate them. There are many different solutions out there. There's Docker Swarm, there's stuff like Mesosphere. We've played with Kubernetes. It's from Google initially, written by a guy called Brendan Burns, who now works for Microsoft on the Azure platform. So you can also run Kubernetes on Azure at the moment, which is really nice. So containers solve the issue of deterministic environment, and orchestration allows you to do whatever you want with them. It abstracts your underlying physical hardware from what your needs as an application developer to deploy them. So you as a developer don't need to care what hardware you have available as long as it's sufficient to run your app. It does network management. So in one Kubernetes cluster, you have internal addresses as well as external IPs that you can expose, such that we can run a web client to connect to that cluster, as well as easy environment provisioning. So with one command, you saw I could scale up instances, and I will show you now what else we can play with. So, for our app, we're told that our 15-minute session expired, so we don't use too much resources. But let's go back again. OK, so let's try spinning up a new environment from scratch. We know that we have a web server to host the web content. We have the microservices, and we have the broker, as well as the event store. So what do I need to provision a new environment? All I need is this. I'm going to call deploy. For example, if my company has a new employee and they want to spin up their own environment to play with, and he wants to name it after himself. So if my company hired Neymar, if we can afford him, we know the Docker version of all our artifacts. So again, this will be given to you from a build from a CI server. We can call deploy. And with any luck, we should be able. So this is Kubernetes spinning up. We have configured it to point to Docker Hub, where the Docker images are stored. We have given it the version number that we need. So it's creating public services, both within the cluster and externally. It's now creating replication controllers, which control how many instances of the Kubernetes pods that we want. By default, we want one each of the instances. And after that, we should be up and running. So these are the services, these are the replication controllers, and these are our containers. 2 are still being created, the rest should be running. So with any luck, if we go to webnamer.adaptive, we should have a service running fairly soon. Let's just check the deployment status. Okay, they are all running. Let's hit it again. Ooh. Demigods have showed up. I think the broker has. Let's try something else. Oh, we have something. We have something. Yeah, we have a whole environment, which for a whole end-to-end environment deployment is pretty cool. I'm sure you've worked in places where getting an environment to test your app with has been a pain. Something is down, something's not available. With this, you have the power to spin something up in, what, a minute or less. So
that's about it.
That's it.
So if you want to have a look at the source code, there's the link. Also, if you want to listen to Qiming talk to the guys at .NET Rocks, there's a show there. If you want to follow us on Twitter, that would be probably double my Twitter followers. And yeah, take a look at We Are Adaptive. It's a really cool place to work. Thank you very much. Any questions? There's the microphone. Just there. Yeah, yeah.
Hi, hello. I have a question related with your project. It's just how did you get the service discovery? I mean, and what technology you rely on? You use only the name of the DNS of the service based on the Kubernetes approach?
Yeah, so how do we do the service discovery? Well, each service just identifies itself as pricing dash its instance name, and the client receives that. It might have 3 pricing servers to choose from. Each one of those will have a load that it's sent out that's based on the CPU load, but it could be anything that's kind of relatively.
We can show that.
That's relative.
Yeah.
So yeah, it's all down to this heart beating.
Yeah, we can show that. So that's sort of one of the cool parts of the app. So if you look here, this is quite chatty. We are getting heartbeats from all the backend services. That's the pricing, actually. Let me kill that, and then so we can have a better idea. So we're on dev. We want to kill the pricing because it's too noisy. Okay. Okay. So for example, I don't know if it's big enough. You can see these are heartbeat messages we get. We send the service type, the reference data service, its unique name, reference.guid, as well as time and what its load is. So from that information, the client has everything it needs to know to which one it wants to connect to, and at the same time selecting the lowest load.
Okay, but let's suppose that, for example, the broker needs some kind of security or something like
Sure.
this. Then let's say that all the services need this kind of authentication or something like this. All the service discovery will be only on the broker side.
Yeah.
So how will you define this kind of service names, let's say? So any microservice will be, okay, name it by whatever name you want, but do you have any kind of mechanism to, let's say, I want to change this name of this microservice or something like this? Just to understand if the configuration of if microservices can be updated or change it in real time or more or less real time.
Yeah, we can name them whatever we want. So this client looks for one instance of reference something or pricing something. In terms of security, we can also do that. In terms of security, this is a demo, so the broker is open to anyone to connect. In a real environment, the broker would not be this open. It would live in a Kubernetes cluster without a public IP, and only the client should be allowed to access via a reverse proxy. Like we actually use Nginx to serve up the client code here.
So, but at the end, the question about service discovery is that where will rely all the names of the services? That everything will be on Kubernetes, and then only Kubernetes knows all the services that will be available.
Right. So yeah. So the question was, how do we know the service names?
Yeah.
That will be hard coded to the client.
Okay.
The client would know that it needs reference, blotter, pricing, etc. Yeah.
Anyone else?
Sorry.
Did you say Google?
Sorry.
Where are you deploying this on production? Did
Yep,
you say Google
that's a
Cloud?
very good question. We can show you. Yeah, that should be part of the talk. So I can show you the whole build pipeline as well as deployment. So we build using Circle CI, which is a free Docker build CI server. So this was the build, if you remember, that I deployed, 1796. So firstly, we go through this process for CI on every commit. If you're familiar with Docker images, we start with a base image. So for the .NET stuff, that only has .NET installed, the .NET Core framework installed. And then we would load our .NET code onto that image, commit the container, and then push it to Docker Hub as an artifact. So in these steps, we are loading here the base containers, then we're building with our source code, then we run them. We actually spin up each container to run tests, to run integration tests, again, all in one environment, and then we save them and we push them up to Docker Hub. And then for Kubernetes, when I run the deploy command, I've already logged into Kubernetes via that shell, and then I'm able to tell Kubernetes to look for artifacts on that Docker Hub instance, and then I'm deploying on Google Cloud. So Google Cloud, when we started, that had the best native Kubernetes integration because that's where Kubernetes came from. And in here, we have all the management you could want. So for example, we have a centralized logging system. So this is for adaptive, for the Reactive Trader project. So these are centralized logs for every microservice. If you guys have used other centralized logging like Sec or Graylog, this is the same. You can do your search, you can do a filter for logging. In addition, I can monitor my CPU usage for my cluster hardware. So I have a cluster of 3 nodes running for this demo. If I just pick one of them, there we go. We have a spike where we deployed a new environment. And this is our CPU usage for that cluster box. Again, the power of Kubernetes gives you is that everything we can react, again, going back to reactive principles, we can react to any instance here. So we can make a setting. We can say to Kubernetes, if my CPU load goes beyond 70%, then spin up more virtual machines or redistribute my containers so that any container with a particularly demanding load will be moved on his own machine. So that all that is handled for you. You don't need to worry about it.
So just to be clear, we've got 3 nodes that are running. On top of that, it's running Kubernetes. So our pods could be running on any one of those nodes. So Kubernetes can actually do some quite clever stuff around balancing the pods, moving them from one cluster node to another. Yeah, it's quite smart stuff. I think Kubernetes is an open source version of what Google used to manage their infrastructure.
Yeah.
So it's cool stuff.
Yeah, and it's open now, so any way you can run Docker, you should be able to run Kubernetes.
The decision to use Kubernetes as an orchestrator.
Sorry, can you speak up?
The decision to use Kubernetes as the orchestrator for Docker was related with the cloud solution, one of the cloud solutions you have, or why did you choose Kubernetes instead of Swarm, for example?
Yeah. So the question was, why did we choose Kubernetes? It was the most feature complete solution at the time. So we started this project last year around April time, something like that. That's where it started, and it gave us, it was the most at that time was the most well supported, and the tooling from Google was most complete as well. I think we would look into its portability, so deployment on AWS and Azure as well. But again, it's all open source. It's all very well documented as well, and very easily accessible. If you want to play around, there's also something called Minikube, which you can run a local Kubernetes cluster. So you don't even need a Google Cloud account or anything.
Okay, thanks.
But yeah, a year ago there just weren't, I don't think Docker Swarm existed.
No.
There weren't many tools to orchestrate Docker components. Anyone else?
How do you deal with hardware load balancers?
Sorry?
With hardware load balancers, for example.
So we don't do any load balancing against the broker. The client will connect. I mean, if we were going to do that, the client could connect to one of many brokers, and the client would store that configuration. But then the load balancing between microservices happens kind of naturally as a result. You saw in the message before, when the servers send their heartbeats, they report their load, and the client will make a decision based on which heartbeat it's received and what the lowest load of the servers it knows about is. And so load balancing happens naturally.
But the front end is different. It's static.
Oh, I see. Oh, yeah. So we serve up the. Sorry. So the question is, how do we kind of serve the static content?
No. If you have a load balancer like an F5, you need to balance, to set the balancing between the front end point of the entrance of the main page.
So we don't.
Part is managed with Kubernetes, talking with the load balancer, or it's different?
So we don't have any explicit load balancing there. The client knows about a well-known endpoint for the broker, and so there's no load balancing in an F5 sense. Load balancing, when it comes to doing WebSocket connections and the failover for those kind of services, connecting to the broker, putting a load balancer in the way causes quite a lot of trouble. So we kind of tend to try and avoid it and just let the client know about the nodes that it's going to connect to.
So in first place, thank you for the talk. It was very interesting. I've been hearing about the microservices for a while now, but I think I still don't get it exactly. So we could say that a microservice is a static instance of a class. Like, for example, you develop a service that there is only one instance of it. So when you scale it up, what do you exactly do? Like
Sure.
you start another machine and run another copy, or you can just put another instance of the same service in the same machine? What is it?
Yeah, so fundamentally, Docker allows you to deploy different containers on the same hardware, and they will be isolated from each other. That's the benefit. But yeah, it will be exactly the same effect as if you started another machine with the same code running. What you have to be careful is managing state between the two. So in Reactive Trader, we've abstracted that onto event store being the source of truth. So each microservice spinning up grabs its state from there. So it doesn't need to be worried about its own state locally. But in effect, yeah, you can spin up as many machines as you want. It'll be the same. From a hardware perspective, that's another advantage of Docker. You're able to achieve the same level of isolation using less hardware resources. You can run as many containers as you can on a single hardware machine to utilize it fully and not having 5 machines running at 2%. Yeah.
So connected with that, you talk about the event store.
Yeah.
You are storing all the events that happen during all the history.
Yeah.
And when you want to start up another service, you can reiterate it, like by reading all the events that ever happen. Can you actually do that?
Sure. We can be a little bit more clever than that. So event store is very fast. I think anecdotally, people have read 10, 20 years worth of data from event store in a few minutes. So for us, the speed is not a problem. If speed is a problem, then we can be more clever at the event store level. We can snapshot, for example, and then read from the last snapshot. Or read. But in this project, we're reading everything from history, like you said, because we have no performance degradation from doing that.
Thank you.
Yeah. Any more questions?
I think if there are any more questions, Qiming and I have been desperate for a beer while we've been doing this, so we'll be by the bar if you've got any more questions. Yeah,
and last word, we've covered a lot of content very, very quickly tonight. As I'm sure you've known. But the good thing is that everything is on GitHub, everything is open source, and every aspect of Reactive Trader, from the front end in React.js to the .NET Core microservices to all our ops, Docker files, deployment scripts, it's all open source, it's all on GitHub. So go play, have fun, and thank you very much.